And welcome back to Chapter 2, Sections 3 and 4. We're going to continue talking about atoms and symbols and things like that. Mostly, we're talking about symbols. All right, the elements of the atom, let's see, the particles, the subatomic particles, let's go ahead and put it that way. You have the proton. It's located in the nucleus. Has a mass of approximately 1 atomic mass unit. An atomic mass unit is a measurement of mass that's appropriate to atoms, where you're dealing with things that are very, very small. I say approximately 1 because it varies depending on the atom. Remember that you have to hold the protons together. It's using what's known as the strong nuclear force to do so. And the strong nuclear force converts a little bit of mass from your protons and neutrons into the energy necessary to hold them together. So the mass of those subatomic particles can vary a little bit. So just think of it as about 1 atomic mass unit. Its mass in actual, in scientific, its mass in the international system is 1.67262 times 10 to the negative 24th grams. All right, it has a 1 plus charge, and that is definite. Let's see, Q. Q is a symbol for charge, sometimes. All right, and it is the identity of the atom in question. It gives it, it defines the element, okay? Every atom of an element has the same number of protons, and that's represented by Z, the atomic number. Okay, that's just the number of protons. And because it's a matter of counting, it's going to have an infinite number of significant figures. It's an exact number. All right. Next up, we have the neutron, a charge of 0, also located in the nucleus. Its purpose is glue, to hold the atom together. Its mass is likewise about 1 atomic mass unit. But when you look at the actual numbers, 1.67493 times 10 to the negative 24th grams. Almost, but not quite the same as the as the proton. All right. It is represented indirectly by A. Okay, the atomic mass number. Okay. Atomic mass number is equal to the number of protons plus the number of neutrons. So the A minus Z, that's protons and neutrons minus the number of protons. A minus Z leaves you with the number of neutrons. There might be a better way to think about things like this, but this is the way we've been doing it for a century, and we're probably not going to change it. And finally, we have the electron. Let's go ahead and just clear out the space. The electron, charge of -1. It is outside the nucleus, and it gives the atom its personality. Let's see, gives the atom its personality, easily added to or taken from the atom. Which changes the chemical behavior. So a sodium atom with a neutral charge is going to behave differently from a sodium ion with a 1 plus charge. The number of electrons is represented indirectly. It's represented indirectly by the charge of the atom. Speaking of which, ion equals atom with charge. A positive charge means you have lost electrons. Negative means you've gained electrons. Then that, of course, is because electrons have a negative charge. You take away a negative charge, you are left with a positive charge. You add more negative charge, you have negative charge. So, if Q is your charge, then Z minus Q is the number of electrons. Okay, so let's look at, say, carbon with a 2+ charge and carbon with a 2- charge. Well, carbon has 6 protons. Okay, so Z is 6. So 6 minus 2 equals 4. Okay, it's lost 2 electrons, leaving it with a positive 2 charge. On the other hand, 6 minus negative 2 equals 8. So it has a total of 8 electrons. It has gained 2 electrons to give it the negative 2 charge. It starts with, for a neutral atom, it starts with 6e- is neutral. Okay, 6 electrons, 6 protons would give it a charge of 0 for a neutral atom. Now that I've shown you an example, let's talk about chemical symbols. Because you don't want to have to write out the name of the element every damn time you write it down and talk about it. So, let's take a look at the periodic table. All of these are your chemical symbols. They are 1 or 2 letters that are the abbreviation for the element in question. Okay, some of them are obvious. Hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, helium, argon. Some of these are incredibly obvious, but sodium, not so much. It's number 11 down here. How do you get Na for sodium? How do you get K for potassium? Darn it. Get rid of that. So I mean, these are possible to explain. Sodium is from Latin. It's natrium, Natrium. That's just the Latin for sodium. Potassium, that actually comes to us from Arabic. The word alkalia means plant ashes, which might seem a little bit obscure until you realize that the name potassium in English comes from the word potash. That is just plant ashes or wood ash. Because when you burn wood and you collect the ashes, that's potash, and you use that to make soap. You get potassium hydroxide out of that. Likewise, alkalia gives us the names alkali and alkaline earth for these 2 columns over here on the left. And those are the metals that form most of our strong bases. And that's also why we use the word alkaline to talk about things that are basic. So the Arabic is important-ish there. Other examples, iron is ferrum from Latin, gold is aurum from Latin, silver is Ag for argentum from Latin. You seeing a trend here? So as you can see, there are more than 100 elements, and their symbols range from obvious to not so much with the being obvious. You'll learn them over time, and I'll be forcing you to learn them a little bit. So that's one of the ways you'll learn them. The other way, the better way to learn something is just by getting used to it and using it, and talking about it over and over again, which is why I can recognize the elements by looking at them, and you can't. I've been doing this for a long time. That's all. But using your chemical symbol, you can get all of your information in one spot. So if you have the letter X, down here you will have Z. That's the number of protons. Up here you'll have A, and over here you'll have Q. So any one of these can be left off, or even all of them, depending on the situation. These two, the chemical symbol and the number of protons, are synonymous. They both identify the element. So Z is very often left off. A, up here in the left, that is often left off just because we don't always care about the number of neutrons. It doesn't affect the chemistry. Q is only left off if we're talking about a neutral atom. We prefer not to clutter things up because that makes it difficult to read things. So a neutral atom, is just the normal state of the atom, so we don't include that all the time. We usually don't. If it's a neutral charge, if it's a zero charge, we just won't write the zero. We'll write 1 plus or 1 minus or 2 plus or what have you, but not 0. So, for example, this would be something we would often write. Iron 3 plus. That's an iron atom that's lost 3 of its electrons, leaving it with a positive 3 charge. We don't bother with the atomic number. Let's see if I can recall that off the top of my head. Let's go ahead with 22. I might be wrong. Yes, I was wrong. It is 26. And then a common isotope of that would be 56. So that would be something that you could have. Iron 56 with the 3 plus charge. But, we very often wouldn't include that. And unless we had specific reason to be talking about a particular isotope, we probably wouldn't include that. But we would have to include the charge because iron 3 plus is very different from iron 2 plus. That's a capital F, which is also different from, just a neutral iron. Okay, so the charge is pretty much always included. It's just that here it's invisible. Okay, it's there. We just don't see it. It's a neutral charge. So with chemical symbols firmly under our belt, let's go ahead and talk about the chemical formula. Chemical formula is a way of representing compounds. And there's my abbreviation for compounds, CMPDS. Leaves out all the vowels and at least one consonant. So a chemical formula represents a compound. So for example, instead of writing out carbon dioxide, we can just write CO2. Instead of writing out sodium chloride for table salt, we can just write out NaCl. And instead of trying to write out the full name of table sugar, we can just write C6H12O6. So that is your chemical formula. It is just what atoms are involved in that compound, what elements I should say, and how many atoms of each element within that compound. Now, there are complications. We'll be talking about molecular, ionic, and metallic compounds later on, and those take advantage of the abbreviation that is a chemical formula. They have slightly different ways of interacting with that. But this is a very useful, very powerful shorthand. Just the number of elements, or each element that's involved is included. Any element that's not there isn't part of the compound. And then the number of atoms of that element are written as a subscript to the right. Okay. You'll notice that the number 1 is left invisible. Again, like I said, we want to avoid clutter. So if it's not important to include something, we won't. And if the element is written, you can assume there's at least one atom of that element there. So that's why we don't write the number 1 as a subscript. One unfortunate thing about a chemical formula like this is it has no structural information. It doesn't tell us how the atoms are connected to one another. And that can make a pretty big difference. You get things that are called isomers. They have same formula with a different structure. And that can have a big impact on chemical activity, on reactivity, and so on. You can have even very, very minute differences in structure. can have a huge impact. The older members of my audience, you might remember a thing called thalidomide, which was mentioned in a popular song, "We Didn't Start the Fire," Children of Thalidomide. Thalidomide was marketed as a drug to take to ease some of the less pleasant symptoms of pregnancy. It was very good at suppressing morning sickness, which, if you've ever been around a pregnant woman, you'll know that sometimes morning sickness can be debilitating. Sometimes it can reach levels of being almost fatal, just because she can't keep anything, food or water, down. So thalidomide was marketed heavily. It was very, very popular until it turned out that a very, very slight, almost indetectable structural difference between two very slightly different versions of thalidomide had a big impact. One version was a powerful antiemetic. It was good for morning sickness. The other version was a powerful antiemetic that also caused birth defects. It prevented the growth of the long bones, so you ended up with children being born with stunted or missing limbs. And it caused a big uproar there in the 1960s. So, yeah, that structural info can be pretty darn important. And chemical formula just doesn't have it. There are ways of representing structure, so we will be getting to that. Just wanted to let you know, structure matters. The chemical formula doesn't have it. Now, let's go ahead and talk about the empirical formula. The empirical formula is somewhat different in that it is just a ratio. Okay? So, the chemical formula for sugar is C6H12O6. It's the chemical formula. The empirical formula is CH2O. Because, 6, 12, and 6 are all divisible by 6. It's just the ratio of the different atoms to one another. There are a couple of reasons that we would want to consider an empirical formula. First off, an analysis of a compound in order to try and find the chemical formula will start with the empirical formula. Just because of the way it works, you end up with a ratio of the elements to one another, and then from there you can get to the chemical formula. The other reason is that there's a class of compounds, ionic compounds. They always use the empirical formula. There are reasons for that, but ionic compounds, they don't exist in discrete items like a molecule, like carbon dioxide might, or sugar. Instead, they exist as a ratio of ions. So an ionic compound is always presented as an empirical formula. There isn't really... The empirical formula and the chemical formula are always identical for an ionic compound, but that's not true for something like sugar. It has a molecule. Okay, and a molecule of sugar actually is a bundle of 6 carbon, 12 hydrogen, and 6 oxygen bound together in a single unit. Whereas that's not true for something like sodium chloride. Sodium chloride is a thing that's just a ratio, a 1-to-1 ratio of sodium and chlorine. Zinc fluoride, dang it, that should be a capital F. That is a 1-to-2 ratio of zinc and fluoride ions. Okay. So those are the two reasons we care about empirical formula. But all it is a ratio, and you just have to look for, the common factor. In this case, 6, 6, 6. They're all divisible by 6. And sometimes it's obvious, C2H4. The empirical formula is CH2. Other times it might be less obvious. C14H49O7. The common factor there is 7. That's C2H7O. I don't know if that's a real molecule or not. I was just making it up off the top of my head. Now, real quick, I want to talk about subscripts and coefficients. Okay. Subscript is the number written down here to the right. And that tells you how many atoms of that element show up in that formula. You never, ever change these. Okay. If you change those, you are changing the compound. Okay. H2O is not the same thing as H2O2. H2O is water. It's necessary for life. It makes up the majority of your body. H2O2 is hydrogen peroxide. They use it to clean rust off of iron, and they also use it as an antibacterial agent. And occasionally, you can, do things like remove your skin if you're not careful. Okay, very different things. Don't ever change the subscripts. The coefficient is the number written in front of the molecule, or in front of the formula, and that tells you how many times that formula or that molecule or what have you shows up in a particular situation, such as this chemical reaction. And that can change. You are free to change the coefficient. You can never, ever, ever change the subscript. Okay. And coefficient is changed whenever you're balancing chemical reactions, say. Subscripts, no, don't touch. Hands off. Stay away. And finally, let's talk about the structural formula. Structural formula is a formula that shows the structure. So it's literally just drawing the molecule, showing the connections between all of the atoms. Okay. Let's. Okay. So it makes it clear, how everything is linked up, and why, one thing will behave differently from another, even if it has the same chemical formula. And these are two very different things, even though they have the same chemical formula. They have different structures. As you can see, the hydroxide there, the OH, has moved from one end of the molecule to the other, and that changes the chemical behavior of these guys dramatically. So, for example, this here is vinegar. You can put that on a salad. This here would be, let's see, (2-hydroxyacetaldehyde). I have no idea if that would be. I wouldn't put it on my salad just because I don't know what the hell it is. Stay away. Okay, but that's all a structural formula is. It's just a way of drawing the entire molecule with all of the connections between the atoms. This right here is just a two-dimensional sketch, but molecules are actually 3D. So this here has somewhat limited application. You need a way of drawing things in 3 dimensions, and that does exist. And if you continue with chemistry, you'll get into that eventually. If you have access to a program like this, obviously it's fairly straightforward to draw a structural formula, or on a dry erase board or on a piece of paper or what have you. Not so much with an old-fashioned typewriter. So for quite some time, you would not find these in your chemical journals. At least not, pretty versions like we have today. You would have these sort of hand-drawn sketches. Nowadays, there are programs created by and for chemists in order to insert these things into papers and so on. I don't have that. So if you see a structural formula from me, it's probably going to be hand-drawn. These can get more complex, more detailed, and provide more and more information, but you can see that they're a little bit more involved. They take a little bit more effort. But I should hope that they're fairly straightforward. Structural formulas are very, very important for organic chemistry, or Orgo as it's known, or OChem, depending on the school you go to. But they have their own version of the structural formula, and it removes even more information. So, for example, this is vinegar, and this is the 2-hydroxyacetaldehyde. Okay, it removes a whole lot of stuff that the organic chemists just don't care about and leaves the stuff they do care about. It's a very useful, very quick and powerful shorthand, but it takes some getting used to. We definitely won't be covering that this semester. We will be seeing structural formulas, though. And let's see, quick note. Because we'll see it later, I want to go ahead and at least introduce you to it now. Some 3D notation. It's difficult to represent things in 3D, but we do have a way to do that. So here's a carbon atom bound to hydrogen and hydrogen. Those two hydrogens are in the plane of the screen in this case. Okay, so that straight line is just flat on the same plane as the paper, as it were. But then you have these two, hydrogen, that triangle tells you that that bond is coming out of the screen towards you. And that dashed line tells you that the bond is going out toward the back, behind the screen, as it were, behind the page. And that's how we draw things in 3 dimensions, when we want to emphasize the 3-dimensional nature of the things. You will be seeing these more as we start getting into optical isomers. But that's later in the term. It's not immediately important. I just wanted to show it to you. But that's it for this lecture, and I'll see you around.